Okay, everybody, welcome back. Well, this is a problem that you've all been waiting for, or well, if you haven't been waiting for it, at least I've been telling you about it all year. And this is the slide loving pig problem. Now it says it's Bailey's favorite, and actually he introduced this problem to me, but it's really become one of my favorites too. So I give him credit for that. But it's a neat problem. Don't be afraid about how much I've been talking this problem up. It's not so much that it's hard. It's actually kind of interesting how it shakes out at the end. Let's take a look at it. Let's try to make some sense of it, and then we'll take a sort of a course of action for this. What I'm going to do is I'm going to kind of scribble some initial sketches in here, just sort of some givens, and then I'm going to shrink this whole slide down and start writing in the blanks over here. So what you're probably going to want to do is have a whole sheet of paper, probably front and back by the time you're done with it, that you can dedicate to this problem. Okay? So let's go ahead and read it. A slide-loving pig slides down a certain 27-degree incline in twice the time that it would take as if the slide were frictionless. Okay? Find the coefficient of kinetic friction. So that is mu k right here. Now let me kind of read that again. All right. So he slides down a certain incline that has friction in twice the time it would take to slide down the same slide if it were frictionless. So it's kind of like this is what's going on. You have a slide and it's got friction on it. All right. And the same slide, but let's pretend it didn't have friction. All right, so this pig here, all right, so there's a pig, and it has 3 legs in the front for some reason. No, I'll have to erase that because somebody will have some sort of difficulty with that. All right, here's a pig again, sliding down, and so this time here, the time it takes this pig with friction equals 2 times the amount of time it takes without friction. All right, so this one goes down like that. This one goes down twice as fast. So we can say, okay, well, time without friction is 1/2 or 0.5 times the time with friction. By the way, you've probably been noticing that the friction slide I'm denoting with an F with my subscripts. And without friction, I'm just denoting with a 0 or an O. All right? So once again, what are we solving for? We're solving for the coefficient of kinetic friction for the slide that has friction. So here, mu k equals what? That's what we want to know. Okay? Now there are a couple other givens we can sort of assume here. All right, assuming that it's the same slide, we can assume that the displacement down the ramp with friction equals, and I'm going to write this towards the middle, sorry. The displacement down the ramp is going to be the same in both scenarios, all right? Displacement with friction equals displacement without friction, right? Is that fair to assume? We can also say that they both have the same initial velocity. Starting from rest. When you at the top of a slide, you start from rest, don't you? So the initial velocity with friction equals 0 meters per second. And initial velocity without friction is also 0 meters per second. These are some assumptions that we can make. By the way, both of these are equal to 0. All right? But the real key here, and notice the lack of any other givens right here, we are going to come up with an actual answer, an actual value, not just some sort of a general statement. We're going to come with an actual answer. There's an actual right answer to this, but you'll notice that there's not a whole lot given to us here. We have the angle. Right? The angle is the same. Theta is 27 degrees. And we have the time difference, but that's it. But here's where we kind of plan our course of action. All right. Well, what is this chapter about? It's about forces, and we're going to start labeling forces on this pig on both of these slides right here. But the only point of comparison that we have between these is time. So how can we get these into kind of a comparison where we can boil this down to solve for mu k, or the coefficient of kinetic friction? Well, time is related to acceleration. And we have these other kinematic knowns right here. And acceleration is related to net force. So that's going to be where we start. We're going to write a statement for net force for each of these two scenarios, turn that into acceleration, turn acceleration into time, and then we have a direct point of comparison. All right? The only difference is that this time is twice this time. This time takes twice as long to get to the bottom as this one right here. Okay? So, I know we've already gotten started technically, but here's where we're actually going to start breaking this down. So I'm going to take this and I'm going to kind of squeeze it into the upper corner like that. All right? And I'm going to sort of redraw my friction pig and my, hopefully you can see the top of that F right there, friction pig and my non-friction pig. All right, so this one has friction. This one does not. And instead of drawing a pig, I'm just going to draw an egg with legs, all right? A blob with legs right here. That's my pig. And now we can actually start drawing out the forces that are involved in this pig. Well, when we draw any force, when we label any force on any object on an inclined plane, it doesn't move at all if there isn't some sort of weight force, mg. So that's the first thing we're going to draw, mg. We also know that there is a force parallel, right? That mg, that weight force, can be broken into a force parallel. Force parallel. Remember, this is the same pig. And also a force perpendicular, right? Force perpendicular, directed straight into the ramp, force perpendicular. All right? Likewise, if there's a force perpendicular directed into the ramp, there must be some sort of supporting force by the ramp, right? And we call that the normal force. And that's directed straight up. And in this case, the normal force is going to be equal and opposite to the force perpendicular, right? Equal and opposite to the force perpendicular. So there's only one difference between these two scenarios, and that is that the one experiences friction. So on this one right here, this ramp is going to have Fk involved. That's kinetic friction. Friction caused by something moving across something else. So, remember what our plan of action is right here. Make statements about net force that involve acceleration. Relate acceleration to time. And then we have a way that we can compare these two sides and join the two together to into one single equation right here. All right, so let's make statements about the net force of each pig. And what I think I'm going to do first of all is just take this and shrink this down a little bit, because I'm going to start running out of space real quick. All right, can you guys see that okay? That's our diagram that we just did. So let's make a statement about the net force on the pig in each scenario. So the net force with friction, we can always say, is the mass of the pig times, or the mass of the system, times the acceleration with friction, right? And over here on the right-hand side, we can say the net force without friction equals mass of the pig, or mass of the system, times acceleration without friction. That's easy. These are, we might say, global statements about the net force acting on each ramp right there. Okay, but we can also make net force statements with regards to components, right? Net force with friction can also be stated as, I'll write this in green at first, the force parallel, which is really what's driving the pig down the ramp, right? Minus the kinetic friction force, right? Hey, look at that. In there is going to be our coefficient of kinetic friction. That's what we're solving for right there. We're locked up in there. Over on the right-hand side, we just have a statement about the net force without friction, and it's nothing more than just the force parallel driving the pig down the ramp. And that's it. So now that these are in place, we can now set them equal to each other. By the way, I'm just going to write in black from here on out. So we can say that mass, that's not black, is it? That's green. Let's go to black here. Mass times acceleration with friction equals the force parallel. It should be an uppercase. I just messed that up. It should be uppercase F. The force parallel minus the kinetic friction force. All right. Over on the right-hand side, the right-hand scenario, it's simply mass times acceleration without friction equals the force parallel. Okay. So let's just stop right here for a second. All right. Remember that we said our link between the two pigs or the two slides, one with friction, one without, is really time, right? Time is the link, and so this time here is twice this time on this side. So in fact, let's just write this over on the right-hand side. Okay. Time with friction equals 2 times the time without friction. Well, remember we had some kinematics values right here. In fact, you should probably still be able to see them. We wrote that down. We wrote the displacement is the same, and the initial velocity is equal to 0 right here. We should be able to make a statement about what? We should be able to make a statement about acceleration, or well, acceleration is over here, right? If we do that, if we can state time in terms of acceleration, we should be able to substitute that in to that acceleration right there. If you're not sure what I mean, here's what I mean. Look at our givens, or look at our knowns. We've got time, we've got displacement, we've got initial velocity, and we've got acceleration involved right here. What kinematics equation do we have that deals with all those? Well, if you go back and look at them, you'll probably notice one that looks pretty familiar. Displacement equals initial velocity times time plus 1/2 acceleration times time squared, right? That's a squared right there. Well, the good thing about this one is initial velocity. That whole thing goes out, it goes away. And what we'd like to do is we'd like to state this in terms of acceleration. Why? Because if we can state this in terms of acceleration, we can plug everything else that equals acceleration into here and into there. Why would we want to do that? Because it would involve time and has a way that we can compare the two sides and bring them together. All right, so let's go ahead and do that. Let's state this in terms of acceleration. So what I'm going to do is I'm going to do some dividing and multiplying. So acceleration, oops, here we go. Acceleration, that's red. Let's do it in black. Your acceleration is going to be equal to, what happens? Well, we bring a 2 up next to the delta x, right? And we divide by the t squared right there. That's going to be our acceleration. So for each side, we should be able to take, now I'll highlight this in red, this, and take that and stick that in here, right? And stick it in here, because this is our statement for acceleration for each of those scenarios. So we're going to do just that. So I'm going to go switch back to black. So we have mass times what? Well, we have 2 times the displacement over time with friction, right? Because this is the friction side, squared, equals force parallel minus force, kinetic friction force. And over on this side right here, it's just going to be mass times 2 delta x over time without friction squared equals the force parallel. And that's it. All right? So, why was that meaningful? Why did we want to get acceleration out of here and convert it to this bigger, clunkier looking equation? Because this fraction, right, these fractions have time in them. Now if we can take this side, and by the way, I should probably draw a line down the middle here. We're still separating them out. This has time in it. So let's turn these around and solve them for time. All right? And that'll make sense why in just a second. So time is going to come up over onto this side, and this whole mess right here is going to come down into the denominator, I think. So it's going to be mass times 2 times displacement over force parallel minus kinetic friction force equals time with friction squared. All right? And over here on the right-hand side, what's going to happen here? Well, we've got time without friction squared. That's going to come up, and this force parallel is going to come down into the denominator right here, and so it's going to be all equal to mass times 2 times our displacement over force parallel. All right. Well, why is this meaningful right here? Because the times are not equal, but we can now substitute in one time for another, because isn't it true that TF equals 2 times time with friction equals 2 times the time without friction? So what that means is time, I'm going to make that red, I'll make it black again. Time with friction squared equals 2 time with friction squared. See what I did? Right? That equals that, right? So what that means is that, what's the only difference right here? Well, these are almost equal, except this has a 2 squared in front of it, which really means that time with friction squared equals 4 times the time without friction squared, and that's like that. Okay? Which essentially means that this side is equal to this side just with what? Just with a 4 in front of it. That's it. So we're going to rewrite that one more time at the bottom, and then make some little more sense out of it. Okay? Mass times 2 times our displacement over force parallel minus the kinetic friction force equals 4 times m times 2 times the displacement over force parallel. This is big right here, what we just did. I'm going to, oops, I don't want to do that. Well, heck with it. I did it already. Can I erase that? Yeah, there we go. That's huge right there, because now it's going to start getting really easy. It'll get a little messier at first, but then it'll start to get really easy after that. I'm going to take this and continue it up at the top right here. But what we've done right here at the bottom is we've essentially joined these two sides together and set them equal to each other, and really dropped out acceleration and dropped out time, so that we can really solve for the what again? For the kinetic friction force, right? For the coefficient of kinetic friction, which is locked up in there. All right, so what I'm going to do is I'm going to take, let's see if I can take all this stuff. I really want to take that and just make it smaller, and I'm going to move that up to the top right there, because we don't need that stuff anymore. All right, that was just kind of to help us. I'm moving that out of the way. So I'm going to take all this stuff and move it up there. First of all, before I even move all this stuff up, what can we do with some of this stuff? Look at what we have. And look at what knowns we don't have. We don't know mass. We don't know the displacement down the ramp, right? But here's the key. It doesn't matter. Because why? Because they're going to start canceling out. Because mass is in the numerator here. Mass is in the numerator here. 2 times delta x is in the numerator here. 2 times delta x is in the numerator right there. So wow, this got really easy real quick. What I'm going to do is I'm going to multiply, I'll do this in a different color, and orange maybe, multiply this force parallel up to that side, this whole bracket up to that side right there, and I'm going to rewrite it at the top over here. So that's going to be force parallel equals, what is it, 4 times force parallel times, oh, sorry, not times, minus, right? Minus the kinetic friction force. All right? That got a lot easier. Look, only 2 steps ago we were down here. We had this all this junk right here. That boiled down really easily. Okay? Now we need to know, use a little bit of our knowledge about how we can describe these force parallels and the kinetic friction force with respect to each other. Because after all, these can be explained in a little more detail. What is our definition for force parallel right here? Well, it is mg times the sine of theta, isn't it? Equals 4 times, there it is again, mg sine theta. Mg sine theta minus, all right, how do we take our kinetic friction force and open that up? How do we, what's our definition of that? Well, that is mu k, there it is, that's what we're solving for, times the normal force, right? Times the normal force. And I'm going to attempt to shrink some of this other stuff down and blow this up so I have a little more space so we can do it all on one page right here. You might see some things shift around. Just give me a second here. There we go. Okay, so you're probably thinking, whoa, what just happened right here? Well, I just took all the stuff that was filling up the space and I shrunk it down to this little box and put it below the original diagrams right here. So we have a little more space to work with here. All right. So we have this. This is what's going on. Now, this mu k, this coefficient of kinetic friction, that's what we're solving for right here. But we still need to expand this out a little bit and then make it a little bit simpler than before we finally solve it. All right. So one more time, how can we write this in a little greater detail? Well, we got this. Mg sine theta equals 4 times mg sine theta minus mu k times the normal force. Well, what's the normal force equal to? Well, look up here. The normal force is equal to the force parallel. All right, so let's go ahead and write it. Mg sine theta equals 4 times mg sine theta minus mu k times a force, did I say parallel? I'm sorry. I meant perpendicular, right? Force perpendicular, in many cases, is the normal force, right? But, that can't stay like that. And I'm going to move this over here even a little more. Because a force perpendicular has a more accurate description. And let's write it out again. I think you know what that is. Mg sine theta equals 4 times mg sine theta minus mu k times, what is that force perpendicular? That is mg cosine theta, right? And there we have it. This equation right here is as complicated as it's going to get, and it's only going to get simpler from here on out. Because why? Well, look at this. There's some things that are going to go away real quickly here. Everything is multiplied by mg, right? You could factor out the mg's in here and in here and bring it out front, but they would still cancel out, right? So that mg is going to go away, that mg is going to go away, that mg is going to go away. So it doesn't even matter what what mass the pig has, because it would apply for any pig, big or small, does not matter. Wow, that became a lot easier real quick. So it boils down to sine of theta equals 4 times the sine of theta minus mu k cosine theta. Wow, it became a lot easier. All right. Remember, we're solving for this mu k right here. So what would we do to to kind of get this out of this bracket right here? Well, let's distribute that 4. All right. So I'm going to come down here into the corner here where we have a little bit more space. Sine theta equals 4 sine theta minus 4 mu k cosine theta. It's getting easier. It's getting easier. Let's see here. What I'm going to do is I'm going to take this and I'm going to add this whole thing to the other side because I don't like that minus sign in front of my coefficient here. I'm going to add this to the other side and I'm going to subtract this from this side and bring it over. So it's going to be 4 mu k cosine theta equals 4 sine theta minus sine theta. That's becoming easier. All right. Well, 4 sine theta minus sine theta is just 3 sine theta, right? Okay, so I want to start getting things away from my mu k right here. So I'm going to divide by 4, bring it down here, and divide by cosine theta. So we can say our mu k equals 3 sine theta over 4 cosine theta, which is really 3/4 sine theta over cosine theta. What is sine theta over cosine theta? Well, it's really just 3/4, or I'm going to do it in decimal form, 0.75 times a tangent of theta. What is tangent of theta? That's theta is, that's 27 degrees, right? Stick that right in there. All right, and so that means that we actually have an answer. 0.75 times the tangent of 27 degrees. What is that? That is our answer, and that is our coefficient of kinetic friction, and that is 0.38. And that is the coefficient of friction of the friction side. All right, this side is frictionless. This one has a coefficient of friction, and that's what it is. So you would think that with so little information given to us, how could you possibly get an actual answer? But what we did is we compared two very similar scenarios with just one difference of time, and we're able to boil that down. Look at all this mess right here. A lot of this went away. A lot of this just canceled out, and this right here is our only calculation. Simple. All right, so for that reason, I think this problem is kind of fun. You're probably rolling your eyes right now. Maybe you don't think it's fun, but it's neat how in math many times things just go away because they cancel out. So this is the answer that we're looking for, 0.38. Hopefully you got the same thing that I did. If you followed along, you should have been able to. And if you didn't, just touch base with me and ask me and find out. Maybe we'll try to find out where you went wrong, okay? So that's the slide living pig problem, 0.38. And like I said, it's one of my favorites. So thank you for following along, and I will see you in class. See you on the next one.